Hi everyone, this is going to be a walkthrough, or maybe a jog through, of the third Portals case. I think it's the third, by Grayson. This one had an interesting twist in that the previous cases have had different areas that you can portal between as different sheets in the workbook. This time the different areas were all contained within 400 individual Excel workbooks that were provided in a zip folder, and this caused a bit of a challenge to quite a lot of people, including myself. So I actually only completed the case having restarted once I'd looked up and researched how to do the Power Query. In my case, is what I used to bring all the workbook data together. It's a bit frustrating because I've used Power Query plenty of times before in work to combine files from a folder, but there were some nuances about these files which made it a little bit difficult. I'm not actually going to go through the Power Query now because I think other people will have some good videos on how to do that. So I'm going to go with the here's one I made earlier approach. I mean, you can look at the query if you like. Full disclosure, there's a bit of AI in here. Thing is, when the default Power Query GUI, in my opinion, produces quite bad queries, which are very messy and badly named. So in real life, I would always try to write a bespoke query that actually sort of does the job, but it's not the kind of thing you can do in 5 minutes at the beginning of the case very easily, unless you've done that quite a lot. Anyway, I'm not going to go into details on that, but essentially here is the data that's been brought in, and I brought it into this table. So there were 400 workbooks. Each workbook name was, well, I've called it a cell. It's sort of your location is then that workbook name, and so I've just used text before dot to get the cell out. And then there were two pieces of information in the workbook. There was a single sheet, and the name of the sheet is here. This is what made the standard combine feature of Power Query a bit difficult to use. At least I couldn't get it to work. And then the sheet itself contained a single cell at A1 with another cell address in. And I've called these sheet 2 and cell. I haven't thought of a good way of naming these things, but hopefully it will become clear what they mean as we go through it. Okay, let's get started. So to be honest, actually bring that data in, if you know exactly what you're doing, I suppose you could do it in a couple of minutes. If you don't know what you're doing, it might take you 15 minutes, or you just might not be able to do it at all. Either way, so having done that from the beginning, that will save a lot of time in this case. So I'm also going to import my lambdas. Okay. And this first question is just looking up the column number of a cell address. So I have a lambda to do that. So that won't take long. And then the second question is, what is contained in the file named after the following cell address? So now we have the data all in one table. This is a simple lookup. We're looking up the cell address in the thing I've called tcell. That's the name of the workbook. And we're returning the cell value that's contained in the file, and that's the one I named T2. Congratulations, you have now unlocked the ability to move from one island to another. The file name represents your current position, while the cell address contained in the file is your destination. Okay, so we're in file C3, and we want to make 5 moves. And each move we're going to make is we're going to go to the address of the cell in the sheet of the file that we're in. It's so hard to think about this. And that is going to tell us which file to go to next, and so on and so forth. So this is going to be a reduce formula where we're starting at cell address C3. We're going through a sequence of 5, and we're doing a XLOOKUP, the XLOOKUP we just did actually, of A, the current position, to cell, which is the file name, to the 2, which is the place it takes us to. Close the lambda, close the reduce, that'll give us K18. Let's copy that across. Okay, that's level 3. Level 4, starting from a cell address file name, same thing. What is the minimum number of moves for you to get to a designated destination cell address? So this is pretty similar. So I'm going to copy the formula down. And instead of doing reduce, we want to do a scan because we want to see each position we get to. And instead of doing the sequence through a set number of moves, we'll just put in the maximum number of moves, which is 400. That's the number of sheets we have. And that basically tells us everywhere that we can go from this cell address. And then we simply want to do an X match of this thing, the destination, on that. And that gives us 85. Okay, level 5. What is the sheet name in the file named after the following address? So this is where we've cheated because this is supposed to be medium, but actually we've already got the sheet name, which is quite a tricky thing to do in Power Query. So this is really a very easy question once we have that data. So it's either very easy or impossible, depending on whether you can extract the data or not, basically. And so for this, again, we just need to XLOOKUP the cell, but this time we're returning from the sheet. And so what we're going to find out here is that when you use this method of traveling, that's going through a portal rather than traveling normally in this universe that we're in. So level 6, as we've discovered, we've unlocked the ability to portal from one island to another. File name represents your current position, while the sheet name in the file is the destination traveled to using a portal. We now need to decide on the optimal route to get from a starting cell address to a destination cell address. So you can basically either move through one of the 2 methods that we've been through, using that by either moving from a cell to the 2 position or to moving to the sheet position, which is the portal. It took me quite a long time when I did this live to try to understand what was allowed here, but eventually I did. So essentially, every step we make, we can do one of 2 things. We can use the standard movement or we can use the portal movement. And we can do any combination of those for all the steps. So the way we have to approach this is essentially we just have to say, what are all the possible moves I can go in? And we don't know how many steps it's going to take. So my approach to this was I'll put a nice input cell in and say, well, let's start by saying we might have to go up to 10 steps. And let's try to build all the possible movements that you can go on in 10 steps if you have 2 choices. And so this is a sort of combinatorial thing, but I think my combinatorial lambdas don't quite do this use case, or maybe they do, but I'm not sure how to use them properly. But anyway, the one I use for this is one lambda I've had for a while from financial modeling, which is, for instance, when you have multiple regions or you have multiple products like this, say, and you have small, big, and you want to look at all the combinations of those things which are going to be lines in your model. I have this expand dimensions lambda where you can H stack these various things together. Oops. Comma would be helpful. And it will produce all the combinations of those 3 things. So if we think about this particular problem, what we effectively want to do is we want to have a list of 1s and 2s like this, and we want to say for each one, give me all the possible routes through these, and that's what expand dimensions lambda does. So I just need to create the right size of list of 1s and 2s, and we can do that with a sequence. So we can start with a sequence of let's say the number of columns that we have here, and we're going to move by 0, so we just get lots of 1s, and then we want the 2s underneath, so we just need to add a sequence with 2 rows where we start at 0 and have a step of 1. And that gives us 1, 2, 1, 2, 1, 2, 1, 2, and we can wrap that inside our expand dimensions, and then we get all the possible routes that we can go on, where we go 1, 2, 1, 2, 1, 2, 1, 2, including if we're just going 1s or just going 2s, etc. And once we have that, we can get going. So I will copy that, and then we're going to say let that be our routes. So these are all the possible routes we can go on, and then we want to do a by row of that route. So each row in that array is a possible route we can go on, and we want to do a by row on routes, and we're going to do a lambda where for each row we want to scan. I'm going to do a let just to make things a bit easier. So this is like places we go, and that's going to be a scan from where our starting position through our row, and we're going to do a lambda where we say AV if v equals 1. So let's say if v equals 1 we use the portal, and if v equals 2 we use the normal route. So if it's 1 we can go through the portal from A, look up in cell, returning sheet, and if it's 2 we're going to use the normal travelling, so that's A, look up in cell, returning from 2, close the look up, close the if, close lambda, close the scan, but output. So we can't actually output places from the, well actually if we turn this into a by row we can, can't we? And then we can have a look at it. Places, let, lambda, by row, let. Okay, so these are now all our routes, and for each one, okay, we simply again want to do the lookup of the destination in those places, and I need to close that. And then we're going to get some NAs because some of the time it's not going to get there. So I'm also going to attempt to wrap that in an if error, returning 999, let's say. And so now we'll get, if we don't get there, we'll get 999, and hopefully somewhere down here we will get there. There we go. That one gets there in 10. So now all we need to do is take the minimum of all of these, and we should get there. I don't know if our array is big enough for all answers. Yes, it is. So in fact, we don't have to change it. Nice. Okay. So then moving on to level 7. So level 7, due to excessive use of portals, each person has now been restricted to using portals up to once. So this is essentially the same question, but sometimes, but on each route, we can only use a portal once. So we can essentially use the same formula here, but our routes need to look slightly different. So instead of having every combination of 1 and 2, there are just particular combinations we can use. Actually, and the set is is slightly smaller than the set we had previously. So I'm just going to do another input cell, because again, we're not sure how big it needs to be. But if we start with 10, our roots need to look something like this now. So a sequence of 10 rows and 10 columns with a step of 0. That gives us lots of 1s. And what we want is, we want to have a 2 in every possible position. So all I'm going to do is I'm going to add to that the M unit, which gives the identity matrix, is that what it's called, mathematicians, of this thing. So it just gives 0 everywhere except for on the diagonal where it gives 1, and that gives us a 2 all the way down. I think technically we can have a trick without portals as well. I'm not sure it actually mattered because I got this right without using it before, but so technically we probably should VStack on as well another lot of 1s at the bottom, and I will accept that correction. So there's our portal-less root at the bottom, and now all we need to do is take that, stick it into our roots and go. Now when I did this live I was really stupid, so I built that matrix of 1s and 2s, but I did it on another sheet, and then I turned it into a named range and then referenced that range in the formula, and then I kept having to make it bigger and bigger, and every time my name wasn't dynamic so I had to reselect it, choose a new name, put it back, still wasn't big enough, made it bigger, created a new name. Terrible. And then I couldn't remember what names I'd used and hadn't used, and I kept reusing names. Basically I panicked. So lesson learned, make these things dynamic, so much easier. So now we just have to choose a number big enough that we get rid of all the 999s. 20, I can't remember what number is big enough. 40, oh, we got one left. 50, yay, okay. And that is not level 7. I didn't actually notice that this answer was wrong. And I think why that is, yes, that's why it is, because 1 was my portal and 2 was my 2. So we've only got 1, 2 in each root. So that needs to be my portal. So if v equals 2, then it's the portal, and if it's 1, then it's the 2. Okay. And if we do that, okay, now everything's correct. Good. So let's quickly do some bonuses. How many cell addresses move horizontally or vertically to their destination based on row column number of the cell addresses? So this is simply whether the, let's call this orthog. This is simply whether the row num, I have a lambda for that lazily, of the sheet is equal to row num of cell address. Oh no, hold on, it's not the sheet, it's the 2, isn't it? So it's of the item that's in the worksheet itself, or the column of the 2 is equal to the column of the cell address. Okay, and we should be able to do my count of lambda just does sum of minus minus these things. Count of t orthog. Okay. For each pair of addresses in the file name cell value, calculate the absolute row difference and absolute column difference. So I interpreted this incorrectly doing it live, which may be, yeah, I'm not sure. So this to me reads as calculate the biggest of the row difference or the column difference. It seems that the actual answer is the biggest absolute row difference plus absolute column difference. And when we're doing absolute row difference and absolute plus absolute column difference, that is just the movement distance between those two things if you have a movement lambda. So for instance, that would be the cell distance between that cell and that cell if you can only move orthogonally, which in my cell distance formula is the default movement. And the next bonus is the same thing but with the sheet name, so I'm just going to do that now, and that is the cell distance of the cell and the sheet name. And then we just need to get the maximums of those. So that is dist2, and that is dist sheet. Okay, how many cell addresses destination immediately leads back to itself either through normal movement or portal? So this is one where it turned out that the answer that was put into the platform was incorrect. So I think lots of people probably got it right where it was marked wrong. But I'm going to come back to that after bonus 5, because actually bonus 5 is kind of related. Starting from any cell and without using portals, what is the maximum number of moves required to return to a cell that has already been visited? Count your starting cell as a cell that you have visited. Okay, so to solve this, I'm going to create a new sheet, and I'm going to put down here all the cells that we have. There should be 400 of those, yes. And hold on, we're starting from any cell without using portals. So we're only using the first method of movement. So for each of these, we can do a scan through 400 like we did before. It's a scan from here through. I'm just going to do it dynamically in here. Sequence of 400 lambda AV X lookup A in T cell, turning from T2, close the lambda, close the scan, and that's all the places we can go. And then we just want to know, so I have an nth occurrence lambda, which tells me what is the occurrence of this thing in an array, and it's going to be 1 for a long time, but eventually hopefully we'll get to a 2. Blah 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 blah. I've chosen a long one. Let's go, come on. There we go. We got some 2s. Okay, so eventually we get to 2, which means we've come back to somewhere we've already been. So all we want to do here is we want to do x match of 2 in nth occurrence of that. Okay, and that tells us how many steps we can go before we get back to somewhere we've already been. I'm going to fill down with all of those. And this is where it gets a bit interesting. We don't need to discuss this for the answer. So the answer is the max of these and -1 because it's how many steps you can go without repeating. So the answer is 314. But it was a bit concerning when you first do this and you see that all these numbers are the same. And then you do a bit of debugging and investigation and you think about cell and this is like moves. And if I'm gonna take this scan and put it here. Okay, so have a look at this and then let's do a filter. And what you see is that we have only 4 answers, 3, 15, 80, 4 and 3. And actually these nearly add up to 400. And then you realize, okay, this makes sense. Because what's actually happening is that these portals effectively form loops. And you can only ever be in a single loop. And once you get round that loop, you just start again and you're going around. So there's basically a loop of 315. And so 315 of these cells, or is it 314? I think 315 of these cells will have 315 because they're all on the same loop. And there's a separate loop of 80, and there's a separate loop of 3. So it goes J14, G18. Oh no, that's a loop. That's a loop of 2. Yes. So this one is where you can go 3 moves. Is 2 loops of 2, which is why the numbers don't add up quite to 400. So you can go G14, G18, and then that goes straight back. Likewise, the loop of 4 moves is actually 1 loop of 3. Okay, and so this actually tells us something about bonus 4, which is why I wanted to do that last. So how many cell addresses, file name, destination immediately either through normal movement or portal sheet name? So, well, we just answered that question for normal non-portal movement. So we have these 4 cells, which each go back to the other one. We do the same thing for portal. Oops. Just by changing this to sheet. Same thing here. I'll fill that down. And now these 2. So these 2 go back to each other on portal movement. So we have 4 that go back to one another with normal movement and 2 that go back to each other with portal movement. And that gives a total of 6 for the cell addresses where the destination immediately is back to itself. So you can also work that out through a formula in here. Something like one of these things needs to be true. If I look up 2 in the cell returning from 2, then that basically gives me, that tells me whether any other cells have as their 2 destination my cell, if that makes sense. And you can repeat that 4 times. I also checked, 4 times to check technically all combos. So you could do 2 to sheet, but I don't think there are any that work like that. Sheet going to 2, and then sheet going to sheet. That doesn't work. Oh, because, sorry, I haven't finished the formula. They all need to be equal to the cell, obviously. So that's what we're checking. We're checking, well, whether there are any that link back to ourselves. Okay, and if we do a count of those, we see there are 6, and those are the 6 that we already. Okay, that's the end of that case. Quite a fun one if you're a fan of Power Query, or if you already have the query in your workbook. See you next time.